Hello everyone. So today we are going to be learning another method for solving quadratics called completing the square. And we're going to use what we learned about perfect squares in our last video to help us out. All right, so we're looking at completing the square. Remember in our last video we looked at perfect squares and we saw how if we have a perfect square, for example, x plus 1 squared, we can rewrite that or solve for x by taking the square root of both sides. So it was pretty quick to rewrite it. Again, making sure we have that plus or minus. And then we split it up into two parts and solve from there. So here, for example, x is 0 or x is -2. What if we have a quadratic that's not a perfect square? Let's take a look at x squared plus 6x plus 7. At the end of the last video, we looked at what perfect squares look like with our area model. Let's start setting this up with our area model. So let's say this is equal to 0. We're trying to solve for x. Well, with our area model, we have an x squared to start. X squared, which means we'll have an x on each side. We have 6 x's. So we're going to split that up because we want a square. We want the same number of x's on each side. So 3 x's here, x. Oops. So here we have 3 x's, x. And then we have 7 ones left over. So let's go ahead and write all of those ones. 1, 2, 3, 4, 5, 6, 7. All right, so we have 7 ones left over. So notice here, when we use our area model, we don't end up with a square. And that's because x squared plus 6x plus 7 is not a perfect square. We can't factor it into a polynomial squared. And if we look at our area model, we're pretty close to a perfect square. We're just missing a couple of pieces. So what I want us to think about now is, what if we just added in those pieces? What if we went ahead and said, you know what? Let's go crazy. Let's make a perfect square. If this isn't a perfect square, we're going to make it a perfect square. So we added 2 pieces on. Well, by doing that, we end up with x plus 3 on this side. So now if we multiply 3 and 3, we'll end up with these 9 ones down here. And so when we added 2 on, then we got a perfect square, x plus 3 times x plus 3. And perfect squares are helpful, remember, because when we're solving, we can just take the square root of both sides. So looking back at our original equation up here, x squared plus 6x plus 7 equals 0. We didn't have a perfect square, so we couldn't rewrite it as something squared. So we couldn't solve using square roots. But as we see in our area model, if we add 2 to both sides, then the polynomial that we end up with is x squared plus 6x plus, and now that we've added 2, we have plus 9 equals, and we still have that 2 on the other side, which we'll get back to later. And now that we added that 2 onto the left, we end up with a quadratic that is a perfect square. As we see with our area model, we can rewrite this as x plus 3 times x plus 3, which is x plus 3 squared. So we added something onto both sides to change our quadratic a little bit so that we end up with a perfect square. Then, now that we have a perfect square, we can go ahead and solve by using square roots. We could take the square root of both sides. And as always, we do plus or minus the square root on the right side. The square root cancels out the square down here. So x plus 3 equals plus or minus. And when we have the square root of a number that's not a perfect square, like square root of 2, we're just going to go ahead and leave that in that form for now. So plus or minus square root of 2 and we'll just leave it as that. Finally, x isn't by itself, so we want to split this up into the two situations, the two, the positive and the negative, the two signs. X plus 3 equals positive square root of 2, or x plus 3 equals negative square root of 2. And then just solve by subtracting 3 from both sides. So x equals square root of 2 minus 3, or x equals negative square root of 2 minus 3. And those are our two solutions to our original equation up here. So we added something to both sides to get a perfect square, and then we took the square root of both sides. And because we had a perfect square, it canceled out the square root canceled out the square, and then we could just solve for x. Let's look at another example. Let's say we start off with the quadratic x squared plus 4x plus 1 equals 0. And our task is to solve for x, trying to find what x values will make this equation true. Well, if we start off with our area model, we have an x squared up here. We have 4 x's, so we have to split this up in half. So we're going to put 2 x's here. We're going to put 2 x's here. And then we have one left over. So we have one left over down here. So notice again, we don't have a perfect square. This isn't a square here because we're missing a few parts. So we're going to go ahead and just add in those parts. Let's add in, looks like we need to add in 3 of these ones to make a perfect square. And then, now that we've added in those ones, you can see that we have x plus 2 and x plus 2 on both sides. So using our area model, we created a perfect square. Looking at our equation, what we did was we took x squared plus 4x plus 1, and we added in 3 more ones to end up with a square, 0 plus 3. So on this left side, we have x squared plus 4x plus 4, which, as we see to the left, we can rewrite as x plus 2 times x plus 2, which is also x plus 2 squared. And this left side is just 0 plus 3 is 3. So we made a perfect square on the left. And then now that we have a perfect square, this squared up here, we can go ahead and take the square root of both sides to solve for x. Plus or minus square root of 3. 3 isn't a perfect square, so we'll just leave it square root of 3. So x plus 2 equals positive or negative square root of 3. And x isn't by itself yet, so we're going to go ahead and split that up again. X plus 2 equals positive square root of 3, or x plus 2 equals negative square root of 3. So here we just subtract 2 from both sides. X is negative 2 plus the square root of 3, or x is, here we subtract 2 also, negative 2 minus square root of 3. So this right here is our two solutions to this equation we were given to solve. So now we're done. So we didn't start off with a perfect square, and it kind of feels like cheating, but we just added in a few parts to make a perfect square and make our lives easier, and then we took the square root of both sides. And this is something we can do because with our equation, we added a 3 on the left here, which would normally change the polynomial on the left. But if we add it to both sides, then nothing in our equation changes. So we can transform, add, subtract, multiply both sides by the same thing, and our equation still remains true. So as long as we added that 3 to both sides, we can rewrite our polynomial with 4 as the constant, and then rewrite that as a perfect square. So this is the method that we call completing the square. And it's called that because we're dealing with squares. And an easy way to see that is looking at the area model. We're trying to end up to complete this square. We were missing 3 parts. So we added those 3 in to complete or finish that square. All right, so next, let's take a look at, well, actually, let's look back at our 2 examples. So here we needed to add in 3 parts so that we ended up with 4. So we ended up with 4. We wanted 4 ones over here. Up here, we added in 2 parts so that we could end up with 9. So our goal was to end up with 9. So let's take a look at this orange square down here. The orange square is 9, and it's 9 because each side is 3. So if we look at the constants here and here, we have 3 and 3. So this bottom right square is going to be 3 squared, or 9. So our goal in this case was to make sure that that bottom right square was 9. Down here, our goal was to make sure that we ended up with 2. With 4, because we had a 2 up here and a 2 on the left here. So our goal was to end up with 4. And to get to those goals, we added something to both of our area models. Up here, we added 2 to end up with 9. Down here, we added 3 to end up with 4. And these 2's are half of the x coefficient. And that's because we split up the x's, we wrote them all out, and we had to split them up in half because we needed the same number of x's on both sides. So we could get a square. So completing the square, we could write out the area model every single time. We could also just do this work by using these patterns and noticing these patterns to help us skip the area model so we don't have to write it out every single time. So if we have a quadratic x squared plus bx plus c equals 0, and we're trying to solve this quadratic, let's say this isn't a perfect square, then we want to add or subtract something to make it a perfect square. And if you remember with our area model, what we did was we took our coefficient for x, we split it in half, and then we ended up taking that half, we split it in half here, 2 and 2, and then we ended up taking that half and squaring it. 2 times 2, or 2 squared, is 4. Up here we took our 6, split it in half, 3 and 3. And then the goal, what we wanted to end up with, was 3 squared, which is 9. 3 squared, 2 squared. So our goal is to take b divided by 2 and square it. B divided by 2 squared. So this is our goal for the constant. So that's what we want in this spot here for the c. We want to end up with that b divided by 2 squared. Let's take a look at another example with numbers. I think it's a little bit more clear if we use numbers instead of just b and c. Let's say we have x squared plus 10x plus 16 equals 0. So here, if we try to factor this, we won't end up with a perfect square. If this was a perfect square, we would have x plus 10. Sorry, not x plus 10. We would have x plus 5 on both sides of our area model. And that's so that we end up with 10 total x's. We have 5 x's here and 5 x's here. So we want to end up with 10 total x's. So this bottom corner, the number that we want, our goal, is going to be, we split up the 10 into 2 5s, and then we square those 5s to get 25. So this is 5 squared. So we want to end up with 5 squared, or 25. In other words, we took our b term, 10, we divided it by 2, and then we squared that number. 10 divided by 2 is 5. 5 squared is 25. So 25 is our goal for this part of our quadratic. So, and it's our goal because if we can get that part to be 25, then we end up with a perfect square. We end up with x squared plus 10x plus 25, which we can rewrite as these two factors. So in order to end up with 25, there's two different things we could do. The first method has an extra step, but it can be really helpful when you're starting off with learning completing the square. We have x squared plus 10x plus 16 equals 0. For the first method, we're just going to take whatever we have here and subtract it from both sides. So we're going to take that 16 and subtract it from both sides. That way, the ones place here is just 0. So we have a 0 there. So in order to end up with 25, our goal, well, we have a 0 here, so we need to add 25. And because we have an equation, we need to add 25 to both sides. So adding 25 to both sides, we get x squared plus 10x plus 25 equals negative 16 plus 25 is positive 9. We reached our goal of 25 here, and that's helpful because we can rewrite this as x plus 5 times x plus 5, which is x plus 5 squared. And if we take the square root of both sides, again, making sure we do plus or minus, we get x plus 5 equals plus or minus 3. And as a reminder, x is not by itself, so we need to subtract 5 from both sides. So x plus 5 equals positive 3, or x plus 5 equals negative 3. If we subtract 5 from both sides, we get x equals negative 2, or x equals negative 8. So here we found our two solutions to that quadratic that we started off with, which I rewrote right here. X squared plus 10x plus 16 equals 0. So this is one method. The other method is a little bit similar. Instead of subtracting 16 from both sides, we're going to think about what do we need to add 16 plus what to end up with that goal of 25. So 16 plus 9 gives us 25. So with our equation here, we're going to add 9 to both sides so that we end up with 25 on the left side. So we get the same goal, what we see up here. We end up with the same equation. Here we just need to do a little bit more kind of like mental math. Instead of moving it over and then adding, we need to think about what we need to add to end up with 25. You could also take 25 and just subtract 16. Either way, we end up with this perfect square on the left. We can rewrite that perfect square as a polynomial squared and then use square roots to solve for x. So we're starting off with any quadratic, and a small note, any quadratic with a coefficient of 1. So if we have a coefficient other than 1, we'll talk about that in another video. But any quadratic where we have a coefficient of 1, even if it's not a perfect square, what we can do is just make it a perfect square using this method. And that makes our lives a lot easier because to solve with a perfect square, we just need to take square roots. So I think this video has gone a little bit long, but I want to go over one more example just to make sure that you guys have a few examples of how we can go through this process of completing the square. Here, what I'm going to do is we'll look at the quadratic x squared plus 24x plus 108 equals 0. So on the left here, we don't have a perfect square. We can't factor this into a perfect square. What we can do, however, is add something so that we end up with a perfect square. So you can use either of the two methods we talked about earlier. I'm going to go ahead and subtract 108 from both sides so that we end up with plus 0. And then our goal for that constant is to end up with, well, we take 24, divide it by 2, and then we square that. So 24 divided by 2 is 12. 12 squared is 144. So our goal is to end up with 144. So we're at 0 right now, so we'll just add 144 to both sides. That gives us x squared plus 24x plus 144 equals, on this right side, we're going to end up with 36. Now we do have a perfect square over here. We can rewrite this as x plus 12 times x plus 12 equals 36, which is x plus 12 squared equals 36. And then we can go ahead and undo that square by taking the square root of both sides. So we end up with x plus 12 equals plus or minus 6. And finally, to isolate x, we're going to split this up into our two equations, x plus 12 equals 6, or x plus 12 equals negative 6. And by subtracting 12 from both sides, we end up with x equals negative 6, or x equals negative 18. So we added 36 to both sides to end up with a perfect square. And then we rewrote that perfect square so we can use square roots to solve for x. One way to check and see if you start off with a perfect square is to see if this value, the constant, is already our goal that we're trying to find. So if you started off with x squared plus 2x plus 1, well, in this case, our goal would be to get 2 divided by 2 and square it. So our goal would be to end up with 1, and we're already at that goal here. So we actually started off in this case with a perfect square. We could rewrite this as x plus 1 squared, for example. So that's how we can check to see if we have a perfect square. If we don't, though, then we end up adding a certain value to both sides to end up with a perfect square.